Ever watched a high-end movie intro and wondered how light hits a gold logo perfectly while sparks fly by in slow motion? Imagine you're the artist who made that shot. Your client calls and says they love it, but they want the gold reflection to be exactly 20% brighter. They also need the shadows and those flying sparks to remain exactly as they are. If you rendered that animation as a standard MP4 video or a flat JPEG image, you are out of luck. Adjusting just the reflection on a flat image is like trying to extract the sugar out of a chocolate cake after it's baked. All the ingredients are permanently locked together. High-end studios avoid this by using a file format called OpenEXR. Think of an OpenEXR file like a magical lunchbox. Instead of holding one flat picture, it holds dozens of hidden layers inside a single file. We call this multi-pass compositing. It keeps ingredients separate, like modular Lego blocks we stack. Preserving these raw components of light ensures that every visual decision remains reversible, turning a finished render back into a living, modular workspace. A 3D program builds a scene by generating different passes, which we call AOVs. AOV stands for Arbitrary Output Variable, which is a technical term for a specific layer of rendered data, like shadows or reflections. The first major building block is the diffuse pass. You can think of this as the foundational base color of your object, kind of like the structural red Lego bricks holding up a toy castle. It contains the raw color without any shine or glow. Next, we have the specular pass. This layer contains purely the shiny, reflective light. It sits completely isolated from the base color, capturing only the glossy highlights of the scene. Then there is the emissive pass. This isolates any parts of the image that generate their own light, like glowing sparks or neon signs. This dialog box shows the option for 32-bit float, a critical setting for extracting all these specific channels. 32-bit float allows the file to remember almost infinite shades of light, from absolute darkness to sun-bright pixels, without losing any detail. Separating light into these variables turns a rigid photograph into a flexible environment where you can manipulate every single pixel independently. Having all these separate layers creates a new problem. Putting them back together correctly requires the software to simulate actual physics. To do this, we use a linearized workflow within the ACES CG color space. ACES CG is a universal color encoding system created by the Motion Picture Academy that keeps mathematical calculations pure. It forces the computer to calculate light accurately, preventing colors from combining into a muddy gray. Because we are working in this physically accurate space, the math to rebuild our image is strictly additive. 1 + 1 = 2. By using the linear dodge or add blending mode, we combine our diffuse, specular, and emissive layers back into the exact image we started with. On a professional project, you might have 50 shots in a sequence. Manually importing, stacking, and adding dozens of these layers for every single shot would consume an artist's entire schedule. To solve this, we write a custom script using JSX code. JSX is a scripting language used by After Effects to automate repetitive tasks. This code acts like a robot chef, instantly reading our OpenEXR files and assembling the layers for us. This menu shows the OpenEXR cache settings we use to make this possible. Optimizing the cache strategy and read buffer size allows the script to read these massive files and build the additive equation stack in just a few seconds. Automating the physics of light shifts the technical burden to the system, allowing the workflow to scale with the complexity of the data. Looking back at our client's opening request, the gold reflection needs to be brightened by 20% while leaving the rest of the image untouched. Because the script has already broken the file apart, the artist simply selects the isolated specular layer and shifts its color. They can make it 20% brighter, or even deep blue, and the sparks and shadows remain completely unchanged. This level of real-time iterative adjustment is possible because the mathematical foundation remains pure and the assembly process is automated. We took an image that was permanently baked together, unpacked its layers using the OpenEXR format, and used script-driven math to stack those Lego blocks of light back into place. Building an automated pipeline replaces manual repetition with technical precision. The system handles the assembly, allowing the artist to focus entirely on the creative outcome.